All right, so we're working in chapter 7. We discussed the source-free RC circuit. In the source-free RC circuit, you're looking at the voltage across your capacitor, which is actually the same as the voltage across the resistor. And you find that you get this equation, V of t equals V naught e to the minus t over RC. This is called the natural response of an RC circuit. And when you plot that, what we call this shape, we call it an exponential decay. So V of t is equal to an initial value V naught. That's the value where the capacitor was at time t equals 0, when it will start to discharge. V naught e to the minus t over RC. So when t is equal to 0, e to the power 0 is 1. So V of 0 is V naught times 1. So you're starting at this value of V naught. And then as t increases, e to the power minus t over something is going to get smaller and smaller and smaller. The exponential keeps getting smaller. So you start at V naught, and then the waveform goes down with this exponential shape. We're going to look today at the general form of this waveform, what we call the general form of an exponential decay. We put it mathematically such that if this is the function a of t is equal to a naught e to the minus t over tau, we say that a naught is the initial value. Tau is what we call the time constant. We explained that last time. If I just go back here, we said RC in this particular equation is called the time constant because if you calculate the units of R multiplied by C, or multiplied by Farad, if you go back to the initial units, you're going to find that it's units of time. And obviously it has to be units of time because you have an e to the power minus t over RC. So t and RC have to have the same units. When you look at it here, this is general form. And I'm going to plot it in terms of multiples, like time steps of tau. Or it's like, are we back on? Yeah. Okay. So how do we understand this exponential decay shape? I'm going to assume that, as I mentioned, the x-axis is in terms of tau. Tau is a time unit. Tau could be 1 second, tau could be 1 minute, tau could be 10 seconds, tau could be whatever. So I'm going to say 1 tau, 2 tau, 3 tau on the x-axis, and I'm going to see how does the waveform behave in terms of tau. So when t equals tau, which would be that first time point down there, how much would the waveform be equal to? So a of tau is equal to a naught e to the power minus tau over tau. Okay? If you use that here, okay, you have t here, right? So t now becomes 1 tau, so you have e to the minus tau over tau, e to the minus 1. How much is e to the minus 1? If you look in your calculator and you say, you know, e to the power minus 1, you're going to get a certain value. And wrote all the values down here. So when t is equal to tau, you get e to the negative tau over tau, e to the negative 1. It's this value, which means that you're going to have a function equals to a naught multiplied by 0.36788. Or it's going to be 36.8% of a naught. If you take t equals 2 tau and use it in the equation here, so you get e to the minus 2 tau over tau, so it's e to the minus 2. And you compute that, if it's 2 tau, e to the minus 2 is equal to 0.13534, or 13.5% of the initial value, and so forth. So forth. The value e to the minus t over tau can be calculated regardless of the actual value of tau. Okay, as I mentioned, I don't know if tau is 1 second or if tau is 10 minutes. That doesn't really matter. But when the time is equal to 1 tau, the value of the function is equal to 0.36788 of the initial value. Okay, so what do we find here? Look at that. Now we say that when the time t is equal to tau, the waveform decreased by almost 37% from its initial value. At 2 tau, the waveform decreased to about 13.5% of its initial value. 3 tau, it's close to 5%. 4 tau, it's less than 2%. At t equals 5 tau, you find that the waveform has decayed or decreased all the way down to 0.67% of its initial value. That's really less than 1%, right? Okay. Now, mathematically, you can keep going on forever. Okay, you say, oh, what happens when t is equal to 10 tau? What happens when t is equal to 100 tau? And you're going to have extremely small numbers there, e to the minus whatever. If tau is large, it's going to be very, very, very small. So we are engineers, right? We're not dealing with this in terms of mathematics. We want to deal with it in terms of engineering. So in terms of mathematics, mathematicians tell us that this one is going to decay from initial value of a naught all the way down to 0. It's going to reach 0 at infinity. That's what mathematicians would say. Okay, you can say, oh, what would happen when t is equal to 10 million taus or whatever. Okay, it's going to be such a small number, but it's never going to go to exactly 0 unless you reach infinity. For us as engineers, this is not very useful. We're not going to wait till infinity. We want to know, for all practical purposes, if I have a waveform that has initial value of a naught here, and then it decays like that, how much time should I wait until I would say that, you know, it's gone, the waveform is gone? So we say if it goes below 1% of its original value, then I don't care, you know, about whatever residue is there. As far as we're concerned, if you have a signal, if you have a waveform that became, you know, less than 1% of its original value, then we say, you know what, let's assume that this is gone. This is 0 for us now. Okay, so that's what we say. We say that any exponential decay, if you know what is the value of tau in your equation here, some initial value a naught e to the minus t over tau, if you know how much is tau, then you would know that it takes this shape like that, and when it reaches about, when the time reaches about 5 tau, it would have decreased to less than 1% of its original value. And we would say that's enough for us to assume that it reached its final value here, which is 0. So 5 tau for us is enough to say that we reached the final value. Okay? So again, we're not going to deal with it like mathematician who would say you have to wait until infinity. 5 tau for us is, you know, that's the steady state time that we need. Okay? So we say that from time t equals 0 to time t equals 5 tau, you have what we call a transient response. Okay, that's the response where you have some change. And then once you reach the time, or you go beyond the time t equals to 5 tau, you have reached what we call steady state. Okay? So remember this, this parameter, this number, 5 tau. 5 tau for us is the time the capacitor will take to discharge completely. Completely meaning that the value of the charge on it is going to be so small that it's going to be negligible as far as we are concerned. Less than 1% of what it was at time t equals 0. Okay, now the significance of the time constant, you can have, I drew here 3 different waveforms. The 3 of them are exponential decays. The 3 of them start at the same initial value. You see that they're all starting from the same point. So they have the same A0, that same initial value. But one of them is going to decay much faster than the other. What does that mean in terms of tau? If you have a small value of tau, let's say tau is equal to 1 millisecond, 5 taus is going to be reached in 5 milliseconds. That's fairly fast, comparatively. I mean, it depends on what the other values are, obviously. So we say that you have a small tau, you reach steady state faster. You have a shorter transient time. If you have a large tau, okay, then let's say large tau, tau is equal to 10 seconds, then 5 tau, that's going to take 50 seconds for a capacitor to discharge all the way until it reaches its steady state value. So it's very important for us to know how much tau is. In an RC circuit, tau is the product of R times C. So you find R times C, you know how much is your tau, your time constant, and therefore you can tell how long it will take for your capacitor to discharge completely. It takes 5 taus, 5 times the time constant. Okay, let's look at some other equations. This is the initial circuit with initial, with the original equation, V of t equals V naught e to the minus t over tau, where tau is equal to RC. The current in the resistor is V over R. Okay, so that's straightforward. So I of t, if you want the current, that's V naught over R e to the minus t over tau. How much is the power consumed in the resistor? Power is V squared over R. We have V, or you can say I squared R because you have I now. So it's V naught squared over R e to the minus 2t over tau. 2t because you have a square there. So you have an equation for the power at any point, at any instant in time. You can know how much power is being dissipated in your resistor. And finally, the energy dissipated by the resistor, we're going to integrate from time 0 to time t, p of x dx, and you get 1/2 CV naught square times this bracket, 1 minus e to the minus 2t over tau. So if you want to know how much energy is being dissipated by the resistor from the initial point all the way up to a certain given time t, then you have this equation. So if you wanted to know how much energy is dissipated by the resistor throughout the whole exponential decay, you would do this integration from 0 to infinity. Okay, and then you would instead of t, you would have infinity there, so you would have in that bracket e to the minus infinity. E to the minus infinity is 0, and therefore if time t tends to infinity, you get the total energy dissipated by the resistor. And look at that. You end up having half CV naught squared. Last time, or I mean last chapter, when we looked at the capacitors, we know that in every capacitor that has a voltage V across it, you have energy stored in it, which is equal to half CV squared. So if this capacitor started off with a voltage of V naught across it, then it had some energy stored in the capacitor equal to half CV naught squared. And here we find that at the end of the exponential decay, when all of this voltage is gone, the amount of energy dissipated by the resistor is equal to half CV naught squared. So that tells us that in the, at t equals 0, I had the voltage V naught across my capacitor, and all the energy stored inside the capacitor was half CV naught squared. As currents start to flow, and you have the current IR that we're showing here, which means, there is current in the resistor is going to dissipate energy. The total energy dissipated by the resistor until, the energy is all gone is also half CV naught squared, which makes sense because it shows us that this is a principle of conservation of energy. You had energy stored in the capacitor, half CV naught squared, and then now you have a total energy dissipated by a resistor, which is equal to half CV naught squared. So that's what I was explaining last chapter. The capacitor is an energy storing device. It stores a certain amount of energy, so it takes the energy from the rest of the circuit when it is charging, when it's building up the voltage across its plates. And you have this energy stored inside of your capacitor, which is half CV squared. In this case, half CV naught squared. And then maybe in other situations when this energy is going back from the capacitor into the circuit, the resistors are going to dissipate that energy and take it away, maybe in the form of heat or whatever. So here we're showing that the stored energy in the capacitor, half CV naught squared, is exactly equal to the amount of energy dissipated by a resistor. Example. In the shown circuit, let Vc of 0 equal 15 volts. So we know that your capacitor in this example is initially charged at 15 volts. We want to find Vc of t, Vx of t, and Ix of t for t greater than 0. I'm going to redraw this circuit just to put it in a shape that we're more familiar with. You have here 5 ohm between this node and this one. So I'm going to put it here. That's the same 2 nodes. I didn't change anything in the circuit. At time t equals 0, the capacitor was charged up to 15 volts. Vc of 0 is 15 volts, which is this voltage between these 2 nodes here, right? Vc, well, let's just say Vc. I want to know about Vc of t. Now we understand that the capacitor is going to discharge through these resistors, and Vc of t is going to be equal to like a certain initial value a, e to the minus t over tau, where a is the initial value Vc of 0, that's equal to 15 volts, that's given. And I need to find tau. Tau is Rc. So which R and which C? Now C is known. C, that's 0.1 farad. That's our capacitor here. What is the value of R that I should put to find tau, my time constant? What do you think? Yes, the 12 ohm one. Why? What if I was looking for something else? Would we put another resistor? I mean, the capacitor doesn't know what we're looking for, right? It's just going to behave based on its physics. So the capacitor is going to discharge. into a resistor. Which resistor? What value of the resistor we have? Look, we looked at our, like when we developed the equations, we had the capacitor C and an R like that, and we were looking at the voltage across from them. So the capacitor, that's easy, that's 0.1 farad. Which is the value of R that I should use for my time constant? Which one? Guys, you have a problem here. You have this capacitor that's supposed to discharge. I need to match this one with the situation that we already know. Excuse me? Absolutely, I have to find the equivalent, right? I have to reduce this into one resistance, okay? Because the capacitor is going to be discharging into the equivalent of that. So this here, you have 8 plus 12, that's 20, in parallel with 5, right? So R is equal to 5 in parallel with 8 plus 12. That's 5 parallel with 20. That's 4 ohm. Okay, so R is 4 ohm and C is 0.1 farad. So VC of T is equal to 15 e to the minus T over 0.4. Okay. Or you can say that's 15 e to the minus 2.5 T. Same thing. Instead of saying T divided by 0.4. Okay, that's VC of T. Now I want to find Vx of T. Vc of T is the voltage between this node and this node, right? I want Vx of T, this one. So if I know the voltage between these two, that becomes now a voltage divider equation or problem, because that's 12 ohm, that's 8 ohm. You want this voltage, which is Vx, given that you have this one, which is Vc. Okay, so this is a voltage divider circuit. Vx of T is equal to Vc of T times 12 over 8 plus 12. Okay. Times 6 over 10 times 3 over 5. So that's 9 e to the minus 2.5 T. Okay. Finally, you want the current I flowing through that resistor. Ix of T, that's Ohm's law now. That's Vx of T over 12. So that's 9 over 12 e to the negative 2.5 T, or 9 over 12, that's 1/4. In amps. Any questions? Yes.
Shouldn't 9 over 12 be 0.75?
What did I do? 9 over 7, yeah, sorry, you're right. 3 over 4. Why did I say 0.25? 0.75. Okay. The following example. This one shows you a situation that is a bit, you would think, what do you mean you have a capacitor that is fully charged and then it's discharging in a resistor where there are no sources in the circuit? So how did you get to that situation if there are no sources? So here it shows you exactly how, situations like that arise. You have the circuit with a switch. So look at this circuit, assuming that the switch was closed. So you have a source, 20 volts, and then the 3 ohm resistor connected to the rest of the circuit, the 1 ohm, the 9 ohm, and your capacitor. It says that it had been closed for a long time, meaning you have the switch closed and you look at that circuit and you can analyze it, you can know exactly what's happening with it or in it, until the switch is opened at a given time, and we're going to say that's the time t equals 0. So at t equals 0, you open the switch. When you open the switch, you effectively remove the left-hand side of your circuit completely, because now this branch is not connected. It's like it becomes an open circuit from there on. And you're left with the loop on the right. You're left with the capacitor and those two resistors, 1 ohm and 9 ohm. And so what we need to do here, first of all, I have to find out what happens before we open the switch. Before we open the switch, you have this situation. $20 volts. 3 ohm, 9 ohm, and the capacitor. But we assume that's why it says the switch has been closed for a very long time. It means you have reached DC conditions, everything is stable, your capacitor is fully charged. And we know that a capacitor behaves like an open circuit under DC conditions. So you look at this voltage V. Really relevant, because connect this side of the circuit and then there's nothing on it. There's an open circuit here. So there's no current flowing through this resistor. So there's no drop across it. And if you have a resistor like that with no drop, it means that the voltage V across from here is the same as the voltage across from this side, because obviously this is one node down here, and this node are at the same voltage. There is no voltage difference. The resistor doesn't have a current flowing through it. So the voltage V that we're looking for, which is across your capacitor, is the same as the voltage across the 9 ohm resistor now. So what I need to find out is V before we open the switch, right? That's equal to 20 times 9 over 3 plus 9, another current divider. So that's 20 times 9 over 12. And you have V equals 15 volts. So that's the first part of our solution, is to know how much voltage was on that capacitor before we opened the switch. And we found that you have 15 volts. And you'll notice that it doesn't depend on the value of your capacitor. The capacitor, the 20 millifarad capacitor, doesn't really matter because it behaves like an open circuit at this point. So I have my voltage equal to 15 volts. And then after we open the switch, or after What's the value of R? 10. Okay. These two are in series, and they represent our resistor R. 9 plus 1, that's 10. So I have a V of t, that's 15, e to the minus t over, well, tau is equal to 200 millifarad. 200 millifarad times ohm, so that's 200 milliseconds, right? Which is 0.2 seconds. T over 0.2, which is equal to 15 to the power minus 5t volts. Okay. Last part in this example, last question. Calculate the initial energy stored in the capacitor. The initial energy, that's when the voltage was equal to 15 volts, right? So the initial energy is half C V squared. So we have 1/2 times 200 millifarad times 15 squared. Okay. That's 100 here. That's 15 squared is 225. That's 22.5 joules. Yes. You're right, it's 20. Sorry, because I had 200 here, so I got mistaken. It's 20. You're right. So it's 2.25. Yeah. Okay. Thank you. Yeah, it's 20 millifarad. Thank you. Any questions? Okay, we're going to switch to the second type of first order circuits. We were looking at RC circuits. Now I'm going to look at RL circuits. Now a capacitor keeps its energy or keeps the charge in the form of a voltage, right? That's what, when we looked at the capacitor, we looked at the voltage across the capacitor. That's why we're studying really stores its energy in the form of a magnetic field. The magnetic field is associated with the current, not with a voltage. So here we're going to study this example or this situation by looking at the current I. So the initial current in the inductor is I naught. The inductor has an initial value of current I naught. The energy stored is half L I naught squared. We're going to do a KVL here. So you have VR and VL. Notice that the way it is done in the book is they're assuming that, you know, both VR and VL are written such that the current is flowing through them according to the passive sign convention. So you have VR, you know, plus on the top and minus on the bottom of your resistor, and VL is the opposite, because if you follow the current, then the current flows through your resistor according to passive sign convention, then flows up into your inductor again according to the passive sign convention. But if you wanted to write a KVL, you're going to end up finding that, you know, VR is basically equal to VL with an opposite sign, because just look at them, okay? So you have here VR plus VL equals 0. VL from the inductor is L di dt. VR, Ohm's law, is IR. And you can rewrite that as di by dt plus R over L times I equals 0. So again, you have here a first order differential equation. It looks exactly similar to the differential equation that we had for the RC circuit, except that this time our variable is the current instead of the voltage. The solution of this differential equation, again, is in the shape a to the e minus, in this case, RT over L. And A is the initial current, I naught. So you have here this equation. Now, for the capacitor, we had the voltage is equal to V naught e to the minus T over RC. Here we have the current IT in the inductor that's equal to I naught times e to the minus RT over L. So whatever is in the exponent of your E is a little bit different. And again, this is called the circuit's natural response. So if you look at this particular equation, same thing, it's an exponential decay. That's the natural response of an RL circuit. But the time constant in this case is L over R. And again, we're going to put it in the shape e to the minus t over tau. So the general form e to the minus t over tau is always the shape that we use, except that tau in this case is equal to L over R. Okay. Again, some more equations. What is the voltage across the resistor? I know I of t. It's one current I in the whole circuit. We have an expression for it, I naught e to the minus t over tau, where tau is equal to L over R. You want to find the voltage, use Ohm's law, V equals I times R. So it's I naught R e to the minus t over tau. That's easy. You want to find the power consumed in the resistor, I squared R. So it's I naught squared R e to the minus t over, e to the minus 2t over tau. And then the energy dissipated in the resistor, you end up with this particular equation. And again, I want to know what is the total energy that is going to be dissipated in my resistor at the end of this exponential decay. So if you have an initial current I naught flowing, it's going to continue to flow. It's going to start to get dissipated in your resistor. This is the energy dissipated that in the bottom here. When t tends to infinity, e to the minus 2t over tau becomes e to the minus infinity, that is 0. And you find that the energy dissipated, the total energy dissipated, is going to be equal to half L I naught squared. Again, I'm referring to what we did last chapter. When you have any inductor with a current I flowing through it, the current I determines through it, then it had an energy equal to half L I naught squared. At the end of the exponential decay, we found that the total energy dissipated through the resistor is also the same, half L I naught squared. So the initial energy stored in the inductor in the form of a magnetic field now is getting completely dissipated because the current is flowing through the resistor, which dissipates all that energy. So I'm going to take an example now with an inductor. The switch in the shown circuit has been closed for a long time, so we did one of these before. You know that what you need to do is to look at the circuit before t equals 0, and you consider the circuit as in a DC condition. And then at t equals 0, the switch is open. Calculate I of t for t greater than 0. Okay. So before opening the switch, the circuit and you have here a short circuit because the inductor behaves like a short circuit under. So remember, we've seen that before. When you have a short circuit in parallel with a resistor, no current is going to flow through that resistor. And the current is basically going to flow through the short circuit. That's why it's called a short circuit, by the way. You're shorting that resistor. Which means, now what I want to find out is the value of current flowing here, which is this current I naught. So this circuit basically looks like that. You have 12 ohm here, you have 4 ohm here, and 2 ohm here. And this current I naught is the current flowing through your 4 ohm. So this is I naught. Right? Now to find this current I naught, what I'm going to do, I'm going to first reduce the circuit. I have here 12 parallel with 4, which is 3 ohm. So I have a current here. Let's call that I. I is 40 divided by 2 plus 3. Because I have 2 ohm here in series with the 3 ohm that you have because of this parallel combination. So I have 2 plus 3 is 5. And the current I is going to be equal to 40 divided by 5, which is 8 amps. So this current is 8 amps. I need to find I naught, current divider. I naught, that's the total current A times the opposite resistance, 12 divided by 12 plus 4, which is 6 amps. So you do that before the switch is open. You need to find what is the value of I naught, which is your initial value of current through the inductor. After opening the switch, the left-hand side before the switch disappears, it gets cut out of our circuit, and we're left with a circuit that looks like this. Where you have 12 ohm, 4 ohm, 16 ohm, and our 2 Henry inductor, which had this initial current, like that. Okay. And we're looking for the current I of t. I of t is equal to I naught e to the minus t over tau, where tau equals L over R. L is 2 Henry. How much is R? 8. How did you get that? 12 plus 4 is 16. 16 parallel with 16 is 8. Exactly. So this is 8. So there you go. I of t is equal to 6. That's I naught. E to the minus t over tau. Tau is equal to 2 over 8. That's 0.25. Which gives us 6 e to the minus 4t in amps. Okay. One more example. You have this example, again, with a switch. But this time, it's a little bit different in that the switch is originally open. Okay? The arrow on the switch shows you that you are effectively closing the switch at time t equals 0, not opening it. So before t equals 0, the switch is open and the 10 volt is connected through the 2 ohm to the 3 ohm to the right-hand side of the circuit. So before t equals 0, the switch was open. And I have this circuit, and this here is my I naught. Again, it is shorting this resistance, so the 6 ohm is not going to come into play here. I naught is equal to 10 volts divided by 2 plus 3. That's 2 amps. Okay, so I have my I naught. So now at t equals 0, or after t equals 0, the switch is closed. And I want to show you when you close the switch, you see what happens here? When this switch is closed like that, and you have a short circuit between these two, This short circuit here effectively makes this node and the bottom node 1, right? That's what the short circuit does. And that separates the circuit into two parts. You have the left-hand side here that becomes one closed loop on itself. You have a short circuit here, and then the right-hand side kind of doesn't see the left-hand side anymore because of the closed switch. So if we draw that, that's what you have. And this part here is effectively, I mean, that becomes a loop on its own, and the short circuit here at this point kind of makes, you know, this part of the circuit separate from this part of the circuit. So you don't have to worry about that. We have here 3 ohm, 6 ohm, and 2 Henry. The current here is called I. I'm going to call it I of t, but V naught. I'm going to find these 3 quantities, I naught, V naught, of t. Okay. You have to be careful here. You have an inductor, right? And then these two, basically you have the 6 ohm like that, and the 3 ohm is in parallel with it. So these two together, that's 3 parallel with 6, that's 2 ohm. So the inductor sees an equivalent resistance of 2 ohm. And that's where you can get the tau of the time constant of your circuit, which is L over R. That's 2 over 2 equals 1 second. That's the time constant for this circuit. I of t equals I naught e to the minus t over tau. That's equal to 2, that's I naught that we found here, e to the minus t, and tau is 1. So there you go. This is I of t, which is this one. Okay? Now, this current I of t is going to flow through these two together. I mean, I'm looking at these as one resistor now. So this current I is going to flow through my 2 ohm resistor. I is flowing in the opposite direction. So I naught, it's minus I1. It's minus 6 over 9 is 2/3. With a negative sign there. Okay. Any questions? So you'll have noticed that all of these problems, what you need to do is to know that your parameter, the voltage in case of the capacitor, or the current in the case of the inductor, depends on that equation, which has like A as a formula. Initial value, you have to find that. So it's either given or you have to find it before a switch is opened or closed. So you look at your situation, you look at your problem, you consider DC conditions, you find the voltage across your capacitor or the current through your inductor. That would be your initial condition to use in your equation. Then the other thing that you need is the value of tau. Now, tau for an RC circuit is the product of R times C, and you have the resistor R be the equivalent resistor that you have in that circuit. Just to put it in the shape, I mean, to match it with the original circuit that we derived these equations from. Same thing for the inductor. For the inductor circuit, tau is equal to L over R. Okay. I'm going to move on. We have a definition here that we're going to need. There is a section in the textbook, 7.4, that defines what we call singularity functions. One of them is interesting to us, which is the unit step function. So I'm not going to go into the other singularity functions in that section. The unit step function, which is defined or called u of t, is 0 for negative values of t and 1 for positive values of t. This is, I mean, a special function, u of t. We call it a step function or the unit step function. So this step function, where every time you find u of t used in any of those problems, you know that this is what it means. It means when t is less than 0, this function equals 0. When t is greater than 0, this function is equal to 1. So effectively, this kind of reminds us of what happens in a switch. Okay, if the switch is open, then the current through it is 0. If the switch is closed, then the current can flow through it. So it's kind of like the logic of a switch that you have here. And this is called a unit step function. The step, and then we define something called the step response. The step response of a circuit is its behavior when a DC source is suddenly applied. So if you have a source and it is suddenly applied, it gives you this, this step shape. Okay, now that would be your source, and we call that a step input. So if it's a voltage or a current that was 0, and then all of a sudden it takes on a constant value, we call that a step function. In this case, it would be a step voltage source or a step current source. So we're going to use that in the remainder of this chapter. Section 7.5, step response of an RC circuit. So now we're going to look at an RC circuit, not as we looked before. Before we only had the R and the C alone. What happens when a capacitor, which was charged, and now it is left alone with a resistor, discharges in a resistor without the influence of the source in the happens when I introduce a source suddenly into a circuit. Sometimes we call that the forced response. So we start here. We have this circuit at time t equals 0. I'm going to close the switch. So suddenly there is voltage applied. So that's why we say it's almost like the voltage Vs took the shape of a step voltage. Now it is suddenly there when you close the switch. What happens to the capacitor? You know that you cannot have a capacitor which, say, was originally at 0 volts. It was discharged, and then all of a sudden you have a voltage across it. It cannot jump from a certain value to another in 0 time. The capacitor needs time to charge or to develop the charges across its plates. And we saw that you cannot have a dV/dt going to infinity. So you cannot have a discontinuity in the voltage value. But what we have here, we're going to write that. You have this equation where, just looking at that, if the current through the resistor is IR and the current through the capacitor is IC, they're obviously one and the same. You only have one current in this loop. So IR is equal to IC. Now IR is equal to Vs, that's the source, minus V, which is the voltage across your capacitor, divided by R. And the current through the capacitor is C dV/dt. So now, instead of having IR equals IC, we have this second equation in terms of the voltages. Vs minus V over R equals C dV/dt. You rearrange that, and you get this differential equation. dV/dt plus V over RC equals Vs over RC. If you want to solve that, what is V of t? Now, again, this is the solution of a differential equation. It requires differential equations in math, but this is the answer to that. When t is less than 0, you are left with whatever was on that capacitor before you close the switch. So we say that the capacitor may have had some charge, let's say V naught, and this is our initial condition, our initial value for the capacitor before we apply the step input. But after t equals 0, like when t is greater than 0, then the voltage V of t takes this shape here. Vs plus V naught minus Vs e to the minus t over tau. And I want to dwell on these a little bit. I'm going to take that second equation in this box, and I'm going to draw that, just to try to understand a little bit more what is this equation. So if your capacitor initially had a value of V naught, and then you close that switch, so the capacitor is going to start to charge through that, or because of that new source, from this value of V naught all the way up to the final value, which is Vs, which is the value of that source that you put. And that's what you had, what this represents. Before you close the switch, when t is less than 0, the capacitor had a voltage of V naught. After you close the switch, the capacitor has a voltage of that. That describes your exponential shape. Because we had before, we saw them always going down. The voltage would decay exponentially. We called it an exponential decay, but in this case, it looks like an exponential rise. If the capacitor was not initially charged, if that value of V naught was 0, okay, so you start at 0, and if you take that second equation and you put V naught equals 0 in it, then you have this different form of the equation. Vs times 1 minus e to the minus t over tau. So I just want to show you that here. If you have a waveform like that, V naught, which is here, e to the minus t over tau, that's called an exponential decay. If you have that, let's say I'm starting from 0, I'm going all the way up to a value of V naught. Here, V of t is equal to V naught 1 minus e to the minus t over tau. Okay? And this is called an exponential rise. So just pay attention at these two different waveforms of these two different equations. V naught times the exponential gives an exponential decay. V naught times, in the bracket, 1 minus exponential. Okay. So what happens if you have an exponential rise but that does not start from 0? You get, look to the screen here again on the PowerPoint, the slide. So you have the top part, you have this equation Vs plus V naught minus Vs times e to the minus t over tau. This is how you would describe an exponential rise that does not start from 0. You would start at a certain value and then you go to another value. Okay, we define something here that we call the complete response. What do we mean by complete response? I'm going to look at the complete response in two different ways, just to help us understand it more. The complete response here is defined as the natural response plus the forced response. The natural response is what happens, what we saw earlier in this chapter, when you had a capacitor that was charged with an initial value, and then you let it naturally decay through a resistor. So you have the natural response. This has to do with the stored energy in your capacitor, or same thing for an inductor. But then you may have that happening, and at the same time, you can also maybe introduce a source through this the step input. So you have the step response, and we call that the forced response, happening because of an independent source that you are putting. So now the total response, or the complete response, is both of these happening at the same time. You have to add them up. So look at that. The natural response here, let's say you have your capacitor with an initial value of V naught. The natural response would be this, right? It would decay. It would give an exponential decay. V natural is V naught e to the minus t over tau. That's what you would get if you only had the natural response. Now, what would you have if you only had the forced response? You would have that. Okay, that's what I drew here on the doc cam. If you're starting from 0, forced response with no initial stored energy, you would go with the exponential rise. Okay, V forced is Vs, Vs being the final value up there, times 1 minus e to the minus t over tau. So if you have both of these happening together, the complete response would be adding up those two equations. So if you add them one point in time at a time, it would look like this. You would start at V naught, and then it would go from that point all the way up to the top point. So you add both of these together, and you get Vs plus V naught minus Vs e to the minus t over tau. Okay, so this is how we interpret that particular equation. It's made up of two parts, a natural response plus a forced response. Okay, that's one way to look at it. I'm going to show you another way to look at that same equation, which will come in very handy to solving a variety of problems. I'm going to look at it this way. See, I'm looking at that same equation, Vs plus V naught minus Vs times e to the minus t over tau. But I'm going to look at the complete response as being made up of those two different parts from what we saw before. I'm going to say that the complete response now is made up of those two parts, a temporary part plus a permanent part. The temporary part is the transient response, and the permanent part is the steady state response. And let's interpret that. The transient response is when the voltage is moving with time, okay, going up or going down with this exponential shape. So this part of your equation represents the transient response. You see that? When the voltage is rising, that's the transient. The transient response is represented by the second part of your equation. And the way we do a transient response, look at the step, the difference between V naught minus Vs. You say V naught minus Vs times e to the minus t over tau. That would be the transient response, the part which has the exponential. Anything with e to the minus t over tau is always going to be transient, because after 5 tau, it's going to die away. And then the steady state response is the value that you reach at the very end, which is your Vs. So you add that on top of that, you have this initial value of Vs, and you get the complete response, Vs plus V naught minus Vs times e to the minus t over tau. Okay, I'm going to summarize this now. The complete any equation which has any bracket multiplied by e to the minus t over tau is always transient. And this portion of your equation will always die away and disappear after about 5 tau. And the steady state response is the behavior of the circuit a long time after an external excitation is applied, which means you apply it, you close a switch, you open a switch, you change something in a source, or you introduce a source, or whatever you're doing, and then you wait a long time. A long time for us means more than 5 tau. That's what we call a long time. So the behavior of your circuit after 5 tau, we call that the steady state response. Okay. And therefore, the complete response can be written like this. V of t is V of infinity. Infinity obviously means more than 5 tau, or at the steady state, plus V of 0 minus V of infinity. V of 0 is the initial voltage. The difference between these two is the step. This part is transient. The step multiplied by the exponential, this is going to disappear. Now, if something happens in your circuit, not necessarily at time t equals 0, if I tell you the switch is open at time t equals 5 seconds or something like that, then there's a bit of a shift in the equation. That's why bottom one is the same if it happens at t equals t naught. But that's, I mean, you're not really going to use that bottom. Like we interpreted before. But in this case, I'm not saying voltage or current, because this general equation we're going to discover, it can be used for anything. And we're going to be applying this general equation for RC circuits, RL circuits, with initial condition, without initial condition, natural response, forced response, or step response. This equation really saves the day. So if you don't want to bother t or I, x of t equals x of infinity, that's the steady state or I steady state, plus final value. And I'm putting to solve any. Thank you very much.
It was the summary.
This one?
Yeah. 14.